You might recall the definitions of scalars and vectors from a high school physics class. A scalar is a quantities with just a magnitude, a numerical value, while vectors are quantities described by both magnitude and direction. Vectors wear multiple hats in 3D graphics. They're used to describe velocities, forces, directions, or simply positions in 3D space. You can designate a vector geometrically as an arrow, where the line segment points along the direction of the vector and its length is the vector's magnitude. Under this definition, the tail of a vector has no fixed location. Thus, two vectors are equal if merely their lengths and their directions are the same, as is the case in the two vectors in this image. However, if you fix the tail at the origin of a coordinate system, the vector can describe a position specified by the number of components matching the dimensions of the coordinate system. In 2D space, you describe a vector by x and y components. A position of 2, 1 describes a vector whose head is located 2 units from the origin along the x-axis and 1 unit along the y-axis. This image displays 2D vectors for easy visualization, but the same applies to 3D vectors. In 3D space, you describe a vector by x, y, and z components. This image shows a 2D Cartesian coordinate system, where the x-axis runs horizontally and the y-axis vertically, with positive numbers to the right and up respectively. In 3D space, the z-axis is orthogonal, perpendicular to the x and y axes, with positive numbers running into or out of the screen depending on the handedness of the coordinate system. In a left-handed coordinate system, positive z values move into the screen and move out of the screen for a right-handed coordinate system. A useful mnemonic for handedness is to hold your right hand in front of you, pointing your thumb towards the positive x-axis and your index finger towards the positive y-axis. The direction of your middle finger indicates the positive z values headed out of the screen for a right-handed coordinate system, and conversely for a left-handed coordinate system. Two vectors are added and subtracted component-wise. That is, the operands are drawn from matching components of the two vectors. For example, if you define two vectors a equals a sub x, a sub y, a sub z, and b sub x, b sub y, and b sub z, and perform addition or subtraction between them to produce vector c, then the operations are performed as you see them on the screen. The vector c is equal to a sub x plus b sub x, a sub y plus b sub y, a sub z plus b sub z, the same for subtraction. Multiplication and division are likewise performed component-wise. Similarly, when performing one of these arithmetic operations between a scalar and a vector, the operation is performed component-wise. The following is an example of scalar multiplication, where we have the scalar 4 times the vector a to produce 4 times a sub x, 4 times a sub y, 4 times a sub z. The length or magnitude of a vector can be calculated using the Pythagorean theorem, specifically using the following equation for a three-dimensional vector. So the two pipes there, the bars you see surrounding a, is just notation for the magnitude of a vector, and it's equal to the square root of a sub x squared plus a sub y squared plus a sub z squared. A vector whose length is exactly 1 is called a unit vector. Such vectors are useful for situations that only require the direction of a vector and not its magnitude. When you force a vector to have a length of 1, it's called normalizing the vector, and this is accomplished by dividing the vector by its magnitude. Notice the little hat there above the a, that's the symbol for a unit vector. The dot product between two vectors is the sum of the products of the matching components. This produces a scalar value, hence the dot product is also referred to as the scalar product. Geometrically, the dot product describes an angle between two vectors, and in an equation form, this is the magnitude of a times the magnitude of b times the cosine of the theta, where theta is the angle between the two vectors. If a and b are both unit length, then their magnitudes are 1, so we can drop that component and the dot product a dot b simply becomes cosine theta. From this equation, you can observe the following. If the dot product of a dot b is greater than 0, then the angle between the two vectors is less than 90 degrees. If the dot product is less than 0, then the angle between the vector is greater than 90 degrees, and if the dot product is 0, then the vectors are orthogonal. As you'll see in coming lessons, the dot product has a variety of applications in computer graphics. For instance, the dot product can be used in lighting calculations to determine the angle between the surface and a light source. Another useful vector operation is the cross product. The cross product of two vectors produces a third vector, which is orthogonal to the other two vectors. The equation for cross product is as follows. A cross b is equal to a sub y times b sub z minus a sub z times b sub y. Then the second component is a sub z times b sub x minus a sub x times b sub z. And the third component is a sub x times b sub y minus a sub y times b sub x. You can use the cross product, for example, to compute the surface normal of a triangle, which describes the direction that the triangle faces. We're about finished with this first look at vectors, but before we go, it's important to discuss an aspect of vectors that can be a bit confusing. Remember from the beginning of this lecture that I said that vectors wear multiple hats in 3D graphics. They're used to describe velocities, forces, directions, or simply positions in 3D space. So a vector with the same values can have different meanings. For example, the vector A, which has the values 1, 0, 0, as a position, this can indicate 1 unit along the x-axis, but as a direction, this could represent the direction of the positive x-axis. As a color, it represents the color red, or it can be treated as a force, a velocity, or a set of coefficients. And from a GLSL C++ perspective, a vector is just a set of floats. Recall back to the point demo in lesson 1.4, where we used a vec4 in the GLSL vertex and fragment shaders. That's a 4-float vector, and there are also vec2 and vec3 data types, 4, 2, and 3-float vectors respectively. For C++, OpenGL has no native data structures for representing vectors. But there are a number of quality third-party math libraries, including GLM, the library we'll be using throughout these lessons. And GLM mimics the data types used in GLSL and has analogous vec2, vec3, and vec4 data types. This concludes our first look at vectors. In the next lesson, we'll discuss matrices.